So, I've been working with math, right? And I got this book, Spectrum Math. It's supposed to be for grade 1, which is cool because that's like something, so I can like learn what kids who are grade 1 should be learning. And I'm just looking through this. And I'm looking through their examples, and it's not really that like it's like they've got kids working with number lines, is the thing. And then at the end of this, the thing that caught my eye about this book is they've got this whole, there we go, they've got this whole thing about geometry. And I'm trying to go back, no, I think I went too far back. Geometry. Yeah. So they got this whole thing about geometry here, and they not only cover two-dimensional geometry, but they also cover three-dimensional geometry. And there's this picture here that I see that, like, makes this point that I'm about to make visually for me. And that's 6 triangles make a hexagon. The thing is the thing that goes through my mind is like, oh, if you can, if we think first graders can grasp concepts such as number lines, triangles, and three-dimensional objects, or sorry, in dimensionality in objects, because to understand 3 dimensions you have to understand 2 dimensions. They can understand things like integration, series of number series, and rotations. It's just they're not going to understand it the way an 18-year-old understands it, or a 37-year-old. Awesome. So, here we go. Okay, so they got us working with a number line like this. Right, and I don't know, here, they got us with a 0. Right? Oops, that's weird. It's got a hat. Okay. And it's going to look a little funky, I think, in the final video because of, like, how things shows up. But I'm not going to think about that right now, and I'm just going to, like, go for this and talk about this. So this is just a simple series, and of course, you know, kids are still learning to grasp, like, just simple counting, right? Like, that's all we want kids to do, apparently, at this age, is we just want them to print numbers. That's all we want them to do, is we just want kids to be able to generate numbers in a perfectly iterative pattern. But Phi Day, I think, no, it's coming up because today is the 21st. So Phi Day is Monday. Or it's not necessarily Phi Day, it's Fibonacci Day, but Fibonacci Day can be represented as Phi. So Phi gets 2 days out of the year, which is great because the more chaos we can get, the better. But anyways, Fibonacci Day, right, is coming up. So here's a simple pattern to teach. Here's a simple pattern to teach kids if you can get it right. And instead of iterating your numbers as one step, right? So that was, I'm saying iterate, iterate, because like hopefully all of my math friends out there would be my math friends who took computer science at least, are going to be like, oh, yeah, iterate. So you can iterate because that's all we want out of kids, right? Like that's the way the school system has determined that like math should be taught that you're a tiny computer who's able to calculate numbers really, really quickly in your head, and that you can do that by memorizing them. So here, instead, here's a fun pattern. And let me get back into this. So the pattern we're doing here, right, is each number that I come up with, right, is just is plus, or is, it's, okay, because, like, kids aren't watching this, I can say it. So, to get n, right, to get a number n, we need to know n minus 1 and add that to n minus 2, right? So to get this number, we need to know what this number is and what this number is, and we need to add them together. So the sum of n minus 1 and n minus 2 gives us n. So that, I feel like recursive logic might be, feels like saying like, oh, recursive logic's going to be hard for a child to get. It was not one of the first things we figured out in programming when we were developing programming languages. It took us until I think the 80s before we, like the late 70s, early 80s when we figured out how to start adding recursive language to programming. Or sorry, recursive logic to programming. But at this level, right, like, at this level, it maybe is different from first graders. I don't know, because I haven't worked with first graders. I've worked with 5-year-olds. Like, at this point, 5-year-olds are really just learning how to, like, pick up the chalk and, like, make numbers, because I can sit here and I can print font in, like, whatever silly way I can come up with. Right? But, like, I'm old. I'm just saying. I've got practice at that. So anyways, this is a fun series to work with because they don't have to understand what recursive logic is. They just have to understand that in order to make the next number in the series, you have to add the two numbers before it. So in order to figure out what comes after 13, I have to add 8 plus 13 to get 21. And then I have to add 13 plus 21 to get 34. This is the real test of skill, is when you just like put on the spot and you're like, how well can you add two numbers? Just like you sit here and you just like talk all about this, but can you actually just add? Or do you need a calculator to like figure this out? It's like, ooh, it's getting close. So of course I'm bragging about like, oh, look at my kerning skills, but 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, whatever. 55 is 88. God, this is where it's going to get tricky. 8 plus 5 is 13. 8 plus 5 is also 13. That's such a... wait. Um... Wait, 3 plus 8 is 11. 4 plus 8 is 12. Nope, because... Nope, 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 because you just multiply. That's also not right. Because it's 12. God damn it, that's what I really need. What I need is to be able to just, like... Oh, what I really need to be... Wow, this is good. This gets hard, man. How did you get that? Okay. 11, 8, 9, wow. Etc. Etc. This is a fun number line that you can do with your kids. If you don't even need a chalkboard, you can do it with a piece of paper, and you can just be like, hey, how far in the Fibonacci code can you go? Hey. So I know what I would want to talk. I know what I want to talk about next. Because I already was sitting here and saying, just talking about like triangles and series and stuff, but like real quick. Well, my mind is still on series, I guess. There is another fun game another fun adding game that you can play with children. That's called Pascal's Triangle. No, it's not. I think this is just a binomial distribution, right? I don't even care. Like, there's so many cool things about this. Because because this is the type of crap like I learned when I was like trying to learn how to like work within these concepts of like, I don't even know what, when you start working with like coefficients and variables and like whatnot, like what's that even called? Right, when you start working in these like long form things, and I know there's a bit of probability, but like I learned that at one point, but somebody else like pointed out that like, oh, ones, 1, 2, 3, 4, 5, 6, so that's natural numbers, and then I think
this was something like triangle points, quadrilateral points, and it went up like that, and that was really cool. And then they sort of grabbed this other group of numbers somehow that was like, I can't remember how they did it because it was this weird Facebook post, and they're just like, oh, you can, like, here's all these different series of numbers and stuff. And so, like, that's cool. Of course, like, that's a cool way. Back to one dimension, because we'll get there. We'll talk about dimensionality eventually. But, like, back in one dimension, you know, you've got exponential growth, which is fun. That's a fun series. This is more for your kid who understands multiplication rules. Because to get the next in the series, right, it's an exponent, right? So in this case, what I'm doing is I'm doing what you're doing, what the rule is, the rule is x to the n, where x is the place value, right, and n, nope, sorry, x is the constant, and n represents the place. So, and where n is greater than or equal to 0. Booyah. There we go, baby. That's the rule. That's the rule I'm working with to build this series. Because if you're working with that way, right? There we go. Xn. So here, this is what x is, boop, and this is what n is. 0, 1, 2, 3, 4. So then, to get the next number in the series, right, they would have to know how to calculate sorry, that's not x. Oh, you know what? I was just like, oh, my rule's this. X, n is equal... Oh, f of x equal to x to the n. Oh. Yeah. I can say that. I think I can define it that way. F of x is equal to xn. It's early. It's early, and I wasn't really planning on doing series this morning. Anyways, so if I'm right, f of x is a function generated by taking whatever to the n, right? So then each number here f of some constant variable 2, right? So that's what we're just going to plug into fucking x. And then n's our iterative value, because, like, man, I'm kind of, like, stuttering at the moment with all of this because it's been a long time. My vocabulary might be completely wrong, and that would be a travesty. Anyways, so... back to what I was kind of saying here. To, like, figure out what the next in the series is, it's this exponential growth. So the first number is 1 because 2 to the 0 power equals 1. 2 to the first power equals 2. 2 to the second power equals 4. And 2 to the third power equals 8. 2 to the fourth power, in terms of first grader, would, I don't know, but in terms of, like, teaching of these kids, like, yeah, this is just repeated multiplication. You better not go around telling people I told you it was repeated multiplication. Oh my god. 2 times 2 times 2 times 2 equals... Because it's just 2 times 2, or it's 2 times itself 4 times. So it ends up just becoming... 2 times 2 is 4 is 8 is 16. You can also do this. So it's the reason, so it's not, my brain just went to this place of, like, well, does it fit into recursive logic? Because, like, you can use recursive logic kind of, sort of, in this instant to figure out what the next one's going to be. You can do 2 times 4 equals 8, but that doesn't work again. Because 2 times 8 equals 16, right? So that makes it a little bit easier then to get back on track with a general rule, is because then each one, because then you just double 16 and you get 32, and I'm pretty sure, and that's because, like, each one, right? Because I will let the clever student figure out how you group things in groups of repeated multiplication, but also kind of, like, find that you can just multiply that by 2, and why that would work in this instance of 2 to the n. If you want to have fun, and you want to have fun, and your kid figures this out right away, introduce them to logarithms. Just introduce your child to logarithms. If they figure out exponents too early and they're bored and they need a challenge, teach your kids logarithms. So if your kids made it this far, and your child is just like, oh, I'm bored. Like, we've tackled series, we've tackled the Fibonacci sequence, we have tackled exponents as a numerical series. We have, you have shown me Pascal's triangle, parent. Like, I am now bored. What is there to do now? Well, if they can draw a triangle, and they can, like, generally figure out how to, like, stay close to the curve, we'll say, with that triangle. And I say those kids are ready to learn some integration. Because, hey man, Archimedes was doing this, and your kid is just twice as smart as he ever was, I bet. Maybe. I don't know. But that's all Archimedes ever, that's all of Archimedes' papers are basically just like, hey, how do you draw triangles and then just add the triangles together? Granted, there's another step going on here. Between what I think your child can do and what Archimedes was doing. And that is that Archimedes knew really well how to calculate the various areas of triangles. Because I'm like, oh, if you can draw a triangle, you can do that. You could do some integration. And of course, like, this is the caveat to that rule. It's just like, okay, wait, how well can they memorize area and, like, because I'm having problems drawing triangles actually now on a chalkboard. There we go. And there's another one too, but like I really don't care right now, and I'm not gonna figure out how to draw it because whatever. Anyways. So because to properly do integration the way that Archimedes did integration, right? Because what he would, because I'll talk about that. Because like what he was doing, right, is because he did love this method of being like, you got a circle, and he's like, so he had his own method for like how do you figure out the points along this circle that you're gonna use. Right? And he gave us a general sort of rule of how to do that, and it's based on how Euclid found points across the thing of the circle. So, I mean, if you want to get fancy, you can show him how to do it with a compass and a straight edge. But Archimedes was also an engineer, so it was likely too that he was just working in this proportionality by just like looking at it, right, and just kind of saying it's like, okay, so we have a pulley, right, and we can break that pulley visually into. We can break it down visually into like parts, right? Because this is a ship's because this is a ship's wheel, right? In the real world, or something along that line where it's like, oh, it's designed to just because the design already tells you what it is. It's just like, oh, here's a nut. Fine, screw it, because you're probably doing this with you probably, based on what I'm seeing in spectrum math, your kid's probably working on this already, right? So you have a circle. It's divided into 12 parts. And each of those parts actually have numbers, right? Because what am I talking about? That's right, I'm talking about a clock. I'm talking about a clock, and this is what I'm saying. So, like, visually, right, it breaks itself into into 12, boop. Yep. Nope. Damn it. There we go. Anyways, yeah, it breaks itself into 12 parts naturally. So then the next question you have to ask yourself is, what kind of triangle? So then to sort of build on what he was doing, right? So we already have these 12 points laid out along the visual part of the circle. So now all we have to do, right, is just up here at the top, if we connect these like that, look, you've got a circle. Check it out. Or actually, I guess it's a 12-sided hexagon, right? But it gets pretty close to that curve. So, in that sense, so at that point, there we go. At this point, we need to ask ourselves, like, what type of triangle is this? And how many of these triangles make this up, right? Later you can teach them how to prove that that's... Later maybe you can begin teaching them like different types of proofs about this, but I guess for right now, if you're just like teaching your kids basic triangles and you're just like, here's a triangle, you know, show them this fun trick, because then maybe they won't have a mental breakdown in high school when people then try to like teach them, you know, this sort of thing. Actually, it would have been way more impressive if I actually did memorize triangle. If I actually had my triangle areas memorized, that would have been way more impressive. But yeah, so how many of these triangles make this up? So, and in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Look, it's 12 triangles just like that. Isn't that pretty cool? And so, I mean, if you, the teacher, are working with areas that you yourself already know, like, you're just, because what's fun about this method, as I spent an entire winter, a couple winters back doing, so you get so when you sort of go from Archimedes up into, because Archimedes is like, I think he's like 80 AD or something like that. And so if we want to like jump ahead like a few hundred years to the 1800s, we get this. There's a German guy, and I can't come up with his name. Wittgenstein did his work on these like problems of like irregular circles, and he came up with a very formalized calculus method that I am awful at and I can't do, and I'm not going to show it to you because of that reason. I'm just talking about general history right now. But the basics of what you're doing, right, is you're making potato shapes. You're making potato shapes, and you're asking your kids, like, hey, if we wanted to do what we just did, right? But instead of a circle, we're doing potatoes. Like, how would we break this up? How do we break this potato up into the least amount of regular triangles? Like, the thing is like, because like, this is just a fun game of like what kind of potatoes can you make, and if you really want to like go into this like these methods that I'm talking about, of course, then it would then at a point you're not even talking about like potatoes. You're talking about these potatoes, but you're not just talking about like how do you draw triangles out for this potato. God, there you go. It's not about drawing triangles, but it's more about like trying to make the potato into a symmetrical shape, right? So this is your concave this is your concave region here. And so that was what this guy's method was about, was that when you're doing this, that the best method, right, is to just like, locate your concave regions, flip them across the line, and try to recreate your potato shape as close to a perfect circle as possible. Right? Because as you see, you don't always get a perfect circle. Sometimes you get what looks like a nose or a bump or something on the side. But here's the thing, like, that's much easier now to, like, break down into these equal proportions. Alright, so now you can better guesstimate the area of the damn thing. There we go. Your kid's having fun with geometry already. The next time I do a video like this, I'll show you how music relates to geometry, and then we'll really be cooking with gas. Because then we're talking about adding waves together. But I was talking about three-dimensional and dimensionality, and I kept saying, as I was like working with number lines and Pascal's triangle, I was just like, we'll get back to dimensionality. And so I don't really want to define these ones at these two exactly as a dimension, because like if I do it, I'm gonna get it wrong at this point. Even though I've been warming up. So dimensionality, real quick here. Dimensionality, you get one dimension equals a point. When you put 2 points together and you connect them, you get a line. When you connect two of these, see, this is where it gets tricky. It's trying to define this in this geometric way. But like, yeah, because like you all know, right? And then fourth dimension's time, and fifth dimension is chaos. So, because the fourth dimension is we start connecting two linear points across a fourth dimensional vector that's time, and this whole concept here is dimension 4. See how confusing things get when you put time in, though? When you put the actual time and effort into it and you come up with something like this, like nobody could have predicted what crazy nonsense way that I was actually going to get there. You knew that you knew if I was talking about the concept of time, though, you knew that I was going to get there eventually. And that uncertainty, that craziness, why, my friend, that's simply just chaos. And that's the fifth dimension, is how you're gonna cross this line, nobody fucking knows. Nobody knows. Is this for kids? I can't remember. So, fifth dimension, so, we're not going that high. I'm not going to ask you or your kids to understand anything higher than third dimension. It's just that, like, so the first point I want to make is that third dimension is fun. But, like, you know, because a lot of these are like, trace out this shape. And so I'm going to say, like, you know what's way more fun? And, like, way more, you know, and will, like, give them, and their art teacher will love you forever if you teach them these concepts. If you teach them... If you teach them, you can teach them, like, how to rotate a cube along its axis, along various axes, right? I can't do it that well because, like, I didn't take art heavily in college. I was pretty turned off by it. All of my friends, though, who took art in college, look at some of the stuff that, like, I just know how to do from... Oh! Here's a cool one, too. All of my friends who did do art are like, oh yeah, I recognize that because I took some sort of, like, rendering class or, like, whatever, or engineering class or, like, whatever it was. That's a bad line. Look, I approximated a curve again. Isn't that radical, my friend? But I think you add two logs together. Is how you're doing it. I think. I can't remember. I just remember how to do that. I'm filling people with great confidence. It's just alright to make mistakes and say the wrong answer sometimes. It's just alright to say the wrong answer sometimes and make mistakes. There we go. Anyways, so that's something fun you can do with it. But to go back to triangles, and I wish I had them on me, but something that I've been having fun with recently is like Magna blocks are a thing, and so this is something you can do better with Magna blocks if your kid has Magna blocks. And this is, like, I think this is the best, like, honestly, because, like, actually, let me go grab some, because they're right over here. So, like, here we go. So Magna blocks are fantastic. I have been like messing with these, and like it just makes my brain just like think about all of this crap. And so like they've got like different types of triangles, right? And so, and I just grabbed these three shapes because like they were the first things I grabbed, and I wanted some triangles, and I saw this square. I'm like, oh, okay, but like I can't do with the square like I wanted to show that you can break these squares apart in triangles. I would have actually had to grab 4 of these triangles to do it.
But of course, the other thing, and kids will do this. I've watched a bunch of kids play with these things, and I've seen them all sort of figure out at some point, like, how to, like, build some sort of dome out of triangles. And, like, that's an Archimedes thing. And for those of you parents out there who do like the dice, like to play the dice, you might be aware of the 20-sided dice known as an isosahedron. See if I can. So then it's. It's ugly. It's hideous. No one knows what that is. Anyways, that's me trying to freehand an isosahedron. And it looks god-awful. Anyways, that's one of the many fun things that you can break a triangle down into. Or that you can use, that is one of the many fun things that you can use triangles to make, is these big old regular solids. Because an isosahedron, oh boy, is a 12-sided, if you take a 12-sided regular polygon, because that thing is made up of, like, hexagrams, I think. Pentagons. It's made up of pentagons. It's made up of pentagons. And that's where you get this guy from, is you break those pentagons into triangles. Anyways, that's all my brain can do today. But that's pretty good. That was like that's almost 50 minutes of me just talking about shapes. Like, in a way that I hope, because I am going to post this one to Instagram, but I hope people, see something out of this, because back to what I was going at, I'm like, because quite honestly, this is what I'm trying to say, hopefully, is that if you can sort of like comprehend numbers on a number line, you can comprehend triangles, and you can comprehend, and you can begin to comprehend, the third spatial dimension. Then, and if you can comprehend all this, you can begin to figure out these concepts, to do it at a bigger level, right? Like an actual, like, somebody's paying you to do it, to like sit here and integrate triangles. Like it's like you either need to like memorize the triangles, or you need to write yourself a handy guide that tells you what the triangle sizes are. Something that you can easily and quickly reference when you need it. And that is what I like about the Magna Blocks, is since they have these different types of triangles already, like, that's all you need to do is just offer them like puzzles. Like, can you build a dome out of like this shape of triangle, right? What if you were to build a dome out of this shape? I think this is the easy one to go for. This one's a little bit trickier. And I haven't figured out a good way to do it yet. I can build little ones. That's not true. I have figured out how to build little ones because a 5-year-old taught me. Have a good day.